Okay, so this is an introductory video on algebra, and we're simply going to look at polynomial addition here. So we're only going to use the addition symbol and add our terms together. We'll do subtraction in a separate video. Now I'm going to start with our conventional numbering system, because if we understand very clearly what something like 13 or let's say 201 stand for, then this helps us understand what we're doing when we come to algebra. So 13 can be rewritten 10 add 3, and all we're doing there is we're saying we've got one 10 and three ones. In other words, we're being aware that we have a ones column here and a tens column here. Okay, and here in our second term here we have 200 and 1. So what's this got to do with algebra? Well, the ones column, if I write this as a Roman numeral, then the tens column, so we use X for Roman numerals, the tens column is clearly 10 times the ones column. Okay, gives us our 110. And our next column, the hundreds column, well, normally that would be written in Roman numerals as C, but I'm going to write it as X squared. And this introduces algebra, because what we're doing is we're using a letter, in this case, a letter instead of a number. We're saying 2x squared, in other words 200 is the same as 2x squared. So I can write these now algebraically as 10, which is x, okay, x plus 3. And I can write this as 2x squared plus 1. Okay, well, what's the point of all of this? The point is that if I take this term x plus 3, I'm going to use a curly x now, is I can use a letter to represent any number that I want to add in. And let's say I was a shopkeeper and I wanted to sell everything with a £3 markup. Then I could simply in my spreadsheet say, well, x plus 3, and then each number that I plug into that formula would have 3 added to it. So what we've got here, instead of a fixed x equals 10, which we have in our conventional number system, what I've got here is a variable term. It can be varied. Okay? Any number can be plugged into this term, and that's why we replace numbers with letters. All right, let's just erase that and write out my second term. So my second term was 2x squared plus 1. And again, the x squared here, in this case, simply counted for 100, so it was 2 hundreds. But here, my x squared stands for any number that we plug in squared. So 2x squared plus 1. Let's do a couple more numbers. Say we had 320 then. That would be 300 plus 20 plus nothing, so no ones at all. So that would give me 3x squared plus 2x and no ones. So 3x squared plus 2x. And let's say 451. And that would give me 451 and 50 and 1, giving me 4x squared plus 5x plus 1. Now, if I write that over here, I'm going to get 3 terms 4x squared plus 5x plus 1. And if I've got two terms like these, we would call it a binomial. Now, nomial simply means part, and bi means two, so two part. Here we've got a trinomial. So trinomial means three-part expression. And you'll see why this is important in just one moment. So let's just first of all just erase this terminology here. But it's very important that we learn these. The reason why it's called a polynomial then, because polynomial simply means many parts. So these algebraic expressions can get very long indeed. Okay. Oh, let's just erase the curly brackets as well. Now, if we go back to our addition here, our column addition, we could add these up, and let's in fact do that, so that we get from left to right 200, 300, 400. So let's underline here. 200 add 300 gives us 500, add 400 gives us 900. Here we've got 10, add 20, add 50, so that gives us 80. Whoops. And here we've got 3, add 1 gives us 5. Now how would we express that? Well, our 900 is 9x squared then, because x equals 10. 9x squared. Our 80 gives us 9x. But it's very important that we don't line it up underneath the 9x squared here, because as we can see from here, it goes into that column there. All right, so I'm going to put this over here. Whoops, not 9x, 8x. Okay, so we've got 8x here, and here we've got 5. So in other words, we've got no x squareds here. We've got 0 ones. We've got no x's here and no ones. And we've got no x squareds and no x's and just the 5 here. And that's what we've had to do to line it up. So similarly, if we were to try and add these up just directly, if we were to follow down here, we haven't got them lined up, and so we'd make a mistake. So it's very unusual to see people actually using this method, but I'm going to show you that it's perfectly possible. So if we wrote x plus 3 here, we would then have to write plus 1 there, 2x squared over here, and 0x here. We've now got 3x squared plus 2x, we have to make sure it goes into that column there, plus 0, and our final term simply gets written out, okay, like this. So it might be useful to do that, but we're introducing these 0x terms, which is very unusual, and in algebra we don't tend to do that, and we don't tend to add 0 or subtract 0 either. So conventionally we would write it out horizontally. So let's do that. So we've got x plus 3 plus 2x squared plus 1 plus 3x squared plus 2x plus 4x squared plus 5x plus 1. Now, even though we would tend to write it out horizontally, you can see that this can give us, a really quite difficult challenge. What we've got to do is gather together like terms and keep them in these separate columns. Okay? So we've got to gather together, first of all the x squared terms, and then all the x terms, and then all the ones. So I'm just going to underline our x squared terms here. So I go along the column, and I say, well, here's my x squared, here's another x squared, and here's another x squared. And now we can begin to rewrite this. So what I'm using now is commutativity. In other words, I'm going to change the order, which we can do with addition. So I'm going to write 2x squared plus 3x squared plus 4x squared, and I'm going to use brackets to make sure we associate these together and we don't confuse them with the other terms. Okay, now what I'll do, I think, is erase these underlines, and I'll go through now with the x terms. So I've got an x term here, an x term here, and an x term here. Let's just check above. We've got 1, we don't have an x term there, 2, 3, so 1, 2, 3, so that's correct. Again, using parentheses, so I've got x plus 2x plus 5x. Whoops, let's just erase that bracket, I forgot to write my x. Okay, 5x, and now erasing these underlines. Okay, I should have 1, 2, 3 constants, fixed terms, so with no variables in them. So I've got a 1, there's my 3, and there's my 1. Very easy to miss these. I mean, it does look a jumble, and so you need to be very systematic how you sort these out. But I've got 3, add 1, add 1. I'm just going to write add 5. Okay, let's put brackets around it just to be consistent. So now I can simply add these together, and I've got, well, 6x squared plus 3x squared, that's going to give me 5x squared, plus another 4, 9x squared. So 9x squared, plus 1, so this is 1x, plus 2x, that's 3x, plus 5x gives me 8x, and plus my 5. Okay, so if I go back over here, just finally for comparison, you can see that's exactly what we were going to get here. So if I converted this to algebraic, I've got my 9x squared here, my 8x here, and my 5 here. So there's the relationship between conventional fixed term number addition and the horizontal algebraic addition that we were doing over here. Okay, let's have another go then, because once you get the hang of it, it's quite fun. So what I'm going to do is make up some new terms here. I'm going to, let's say, let's have a trinomial here, so 3-part expression. So we'll have 4x squared plus, let's say, 7x plus 2. Bracket that off. Let's just mark this A and B so we don't get confused. And a binomial expression, let's say 2x squared plus 4. And let's have another binomial, let's say 8x squared plus 7x, let's say. Okay, so quite a long string here. I think what I'll do is just remove the brackets first of all. So just join them all together. So equals 4x squared plus 7x plus 2 plus 2x squared plus 4 plus 8x squared plus 7x. And now let's do some commuting. So we're going to identify first of all of our x terms. So we've got x squared terms rather. So we've got a 4x squared, a 2x squared, and an 8x squared. We haven't written it out now, so we've in columns. So we need to be a bit more careful that we get everything right here. So we've got 3 terms. Yes, that looks to be correct. So we've got 4 plus 2 is 6 plus 8 is 14. So we've got 14x squared. Okay, let's make that clear. Let's erase our underlines now. Now, obviously you might not be able to erase your ink, so you might want to use a different method. But as long as you're systematic, whatever you sort out here should work. So now I've got 7x plus another 7x, so I've got 14x, and I've got 2, add 4, let's just use a different method here. Just let's put a dot under that 2, under that 4, and then just go along the line and check that there aren't any other ones that we've left out. No, there aren't. So plus 6. Okay, so I think we'll leave it there, but I hope that's an interesting or useful introduction to algebraic expressions. The main thing is making sure that we are combining only like terms, and the reason for that is because of this importance that we don't alter the columns, because clearly the x squareds are going to be, well, usually much larger, in this case 10 times larger than the x's, so we're not combining, we can't combine these terms, we've got to keep them in separate columns. When we're going horizontally, we can't see the columns, and that's why people get confused and they're not quite sure what like terms means. But it simply means that we can't move things, we've got to keep things in separate columns, and so we have to make sure that that we're carefully identifying first of all the highest x terms, then the next one, going down until we get to the constants, the single numbers. So I hope that's helpful and makes sense, and it would be a good idea now if you started making up your own expressions, because it's a very simple thing to do, and practice polynomial addition. Right, so the second part of this video, I'm just very briefly going to look at how we would represent the difference between conventional pre-algebraic numbering systems and the algebra that we've started to look at here, and algebra addition. So what is the essential difference? Well, we've seen that there's actually a close relationship between these two things. When we're working algebraically, we're certainly working with numbers. But here, if I'm representing, well, what have we got here? 143, okay? If I'm representing 143, what we can do is measure these numbers or count the blocks. In other words, what we've got here, let's have a look, is we've got 10, so that's 10 times 10, giving us 100 blocks. And that's not going to change, that's invariable, that's constant. Here we've got 10 again, and we've got 4. Okay, we've got 4 rows, so that gives us, let's write it down here, so 10 times 10 equals 100, and here we've got 4 times 10 equals 40, and here of course we've got 3 times 1 giving us 3. So a very conventional, very straightforward thing to understand. What we need to do now though is think of a concrete representation for algebra. What's the essential difference? Well, the essential difference is that we can't measure or count these anymore. So if I get rid of these, let's get rid of the notation here and remove these. Here's our x term, okay? So our x term here in conventional pre-algebraic numbering is fixed, okay? And we can say, we can represent this like this. We can say here x equals 10, and it can't equal anything else. We can count the tens, we can measure the tens. It's always 10. It's fixed. Fixed. Here, this length here can be any length at all. In other words, x is unknown. We don't know what that length is. And yet, and this is the really interesting thing, that doesn't mean we can't perform all sorts of operations and find out all sorts of interesting patterns involving unknown variables. So x in this scenario is variable. And so obviously we're still dealing with numbers here, but there's been a change as we've moved from algebra to, pre-algebra to algebra, we're thinking in a rather different way. In pre-algebra, we tend to want to know what the answer is. We want to calculate a result and we want a number. Here, we're going to have to be satisfied with just looking at the way these terms join together, subtract, multiply, divide. They're going to operate in the same way, but they're going to form patterns and expressions rather than numerical answers. Although we can use then those patterns and formulae, and equations and so on, we can then plug numbers back in to get all sorts of calculations. And we saw that with the x plus 3 example and the shopkeeper who wanted to use that again and again just to add 3 to any number that he put in. So let's have a look now at how this works for addition. Okay. So if we remove this now this length we need to remember could be a very different length indeed. So it doesn't have to be this length here. I've made it shorter, I'm making it longer. It might be, well, it can be any length that we want. So we have to think of it as, I suppose, infinitely elastic. Let's put it back to its shorter size. Okay, and now introduce, so let's have x plus 1. Okay, so we just introduce 1 unit here. Right, so we can describe this dimension here as 1, and here we simply describe this as x, or any other letter that we want to assign to it. And x is very common. Okay, now if I write this out then as x plus 1, where x is variable, what can we say about x squared? Well, x squared is going to be the same length as x, but it's going to be in a square form. Okay? So in other words, it now becomes an area of x along one side and x along this side. Let's look at an example. Okay? So here we have, well, what have we got? Here we've got x squared, exactly the same length as x, but we don't know what length that is. We don't know what length this is. And we don't know what length this is. What we do know, however, is that these question marks are equal. We do know that this is 1, okay? And we do know that this is 1. So we can now write out these expressions. What have we got? X plus 1 here, and we've got x squared plus 1. Let's write it here, x squared plus 1. Here's another x squared, so that seems to be added to this one, so we call this 2x squared plus 1. Okay, so I'm not going to say much more than that, but it's this visualization using algebra tiles is going to be very useful to us in subsequent videos. And you might want to make some algebra tiles for yourself so you can manipulate expressions using concrete representation. Alright, now what I'm going to do then finally is just add these together. So we'll do it using the written method and then we'll do it visually. So what do we expect to get? X plus 1. Now let's actually think about it in column method first. So if we were going to line these up as columns, we would write 2x squared plus no x's plus 1, and then we would add these together. But what I'm going to do is do it horizontal method because that's conventional, so let's just move this down a little bit. Okay, and write it down here. So we've got x plus 1 plus 2x squared plus 1. Gather together any like terms. There's only these numbers that are alike. So we've got now 2x squared plus x plus 2. Okay, so 2x squared, x plus no x's is x plus 2. All right, so if we, let's just erase the notation here in case it gets in the way. Okay, so let's just look at these things visually. So, in addition, all we have to do, obviously, is join these tiles together and then see what we've got. Okay, so if I just move these up, there we go. Now we've got, well, what have we got? We just add them together. So we've got x here. Let's start with the x squared. So we've got 1. Here we go. Let's just draw onto it. I think that'll make things clearer. Okay, so we've got 1x squared here. We've got 1x squared here. We've got an x here, a 1 here, and a 1 here. So added together, we've got 2x squared plus x plus 2. Okay, so I'm not going to say any more than that, but obviously you'll want to practice this. I do suggest that you use pieces of coloured paper and make your own algebra tiles and start manipulating. It's also a good way of generating new expressions. So a very good exercise is to cut out some x squared squares, some x's and some units, plenty of them, and start joining them together, separating them out, and writing down what the expressions are. As soon as you're comfortable, though, with polynomial algebraic addition, move on to the next video, which will be all about subtraction.